Yeah, go ahead.
Okay, welcome everyone to the seminar for finite geometries and groups. So now, today we have the second talk of Ivan Hetman. He's going to continue his presentation of algorithms for constructing Steiner 2 designs. And yeah, Ivan, please go on.
Okay.
Okay.
In the beginning, the question to the audience: do I need to repeat something from previous presentation, or we can go ahead? Actually, this is not very tightly related, but I can repeat some notions. So the question is to you whether you need it.
Well, as far as I'm concerned, you can do a very quick recap of what you've said so far, if it doesn't take too much time.
Okay. So previous in the previous explained how Steiner 2 designs difference families. So from the previous part, what I need it is a structure bit set that is widely used using computers. So this bit set it is just an array of machine words, and using this array you can quickly find, for instance, unions, intersections, differences between the sets, do lexicographical comparisons, and so on. So using these bit sets, we used subsets of the groups in form of the bit sets, and we used specific operations like, for instance, finding multiplication of two subsets, inverse of a subset, or square root of subsets. Also, we considered automorphism group of the group. And currently, we will use automorphism group of so-called G space, which I will define later. And this is basically is it. So also let me remind the definition for base block. So definition of base block is subset B of G is called base block if if B intersecting with a left shift of this subset B cardinality is more than 1, then this block should be equal to this left shift. So why it is important? Because Steiner 2 designs, they have the properties that is complete states that when you have two different points, then there exists only one line that passes through this point. So this property of base blocks guarantees that when we doing left shifts on the base blocks, we will have this axiom of Euclid's these basically are the similarities between today's talk and previous talk. Yeah. So also regarding the base block, there also was a difference family. So let me remind what was the difference family, because my definition of difference family or G spaces will be somehow similar. So a family B of base blocks is a difference family if difference of base blocks are firstly disjoint, and secondly in union they cover all elements of the groups except the neutral element, because neutral element cannot be in the difference of the base block. And also there was an important lemma that for any difference family, union of orbits, I mean the left shifts of base blocks, as a Steiner 2 design. So that's similarities, and everything else will be a little bit different. but still similar. So you will see it in the next part of the presentation. So using these difference families over arbitrary groups, there was possible to generate a lot of new Steiner designs. And I came to the example and the problem. So first of all, that different Steiner 2 designs generated by different families are point transitive, but reverse is not true. So if you have point transitive Steiner designs, it is not necessary that it is generated by specific difference family. So here are examples. Well-known Hermitian unitals and reunitals of order 3. They have point transitive automorphism groups, but we cannot generate them using difference families on any group of order 28, despite the number of points of these unitals is also 28. So I stated the problem on our offline meetings, whether is there a way to generate unitals above using something similar to difference families, and Taras answered to this problem very quickly. So he suggested that I can generate them using G spaces, and that was how eventually we developed the second part of the algorithm, not second part, but second generalization of the algorithm. It is about G space. So these notations and definitions of the G spaces and theorems, they are well known. Basically, I adapted them from the book you advertise it. Also, Vedran, it is the Cameron permutation groups. So if you will look at it, it is very similar to these definitions and theorems. So a G space is a set X endowed with an action G times X to X of a group satisfying the conditions. So there are well-known conditions about the action of the group. So first of all, it should be kind of associative on the action for this group. And second, that neutral element of the group should not move any point of this G space. So this is a generic definition, and let's observe its properties. So first property of G spaces is transitivity again. So transitivity of G space is when by action of the group we can move any point of this G space to any other point of this G space. And also there is a well-known theorem about orbit decomposition that every finite G space is a disjoint union of transitive G spaces. Then we introduced the isomorphism and automorphism of the groups. So isomorphism and automorphisms of G spaces are very similar. So first of all, two G spaces are isomorphic if there is a bijection that preserves the operation. And automorphism group of G space, it just consists of all isomorphisms from this G space to itself. So it is pretty simple, and we can see the similarities. Okay, now let's talk about the structure of G spaces. So first of all, given a subgroup H of a group G, the left coset space, it is a family of left cosets with a action of G given by this formula. So it is also well-known properties of cosets, proved, I suppose, even by Lagrange. And because we have such nice coset space, so coset space is a very simple and powerful example of G spaces. And also, let's note that this G space is transitive. And then important theorems that I will use to structure the algorithm later. So first theorem is that every transitive G space is isomorphic to the coset space G with Gx, where Gx is a stabilizer of any point of x. So this theorem is showing the structure of transitive G spaces. So transitive G spaces, we can consider them as some coset spaces. Okay, then next theorem that shows us what is the relation between isomorphism relation between the coset spaces. So for subgroups H and K of a group G, two coset spaces are isomorphic if and only if H and K are conjugated in G. So this means that if we are building G spaces, we just can consider only one subgroup of a specific conjugation class of a group. And that's basically it. Other you can just skip. And then corollary. Corollary is the following that follows from this previous theorems, that every finite G space of finite cardinality V is determined by a group G and its subgroup H1 and Hn such that sum of cardinalities of coset space is equal to V. This basically gives us information about the structure, how to build G space with specific cardinality V. So this V, it is the number of points of Steiner designs, and this coincidence is not accidentally. This is planned coincidence about this V. Okay, then let's define differences on G spaces. They will be a little bit different as with groups, but properties of them will be very similar. So first of all, let's define the space x squared not equal, which is basically the Cartesian product of x without the diagonal. And for any G space X, this set admits the natural structure of a G space endowed with the action following. That when we act on an ordered pair XY, then we just move this pair to GX and GY. So as you can see, action on a G space X can be extended to X squared. Actually, it can be extended to any cardinality of Cartesian product, not necessarily X squared. And I actually did specific generalizations that also work with bigger cardinalities. But we are talking here about Steiner 2 design, so we need only the set X squared not equal. Okay, now the same definition for the base block, nothing changed. So if we have a subset B of G space X, and this subset is called base block if, again, this property that will make a first Euclidean axiom satisfied. So when we act on this block B with an element G, if it intersects its shift in more than one point, this means that this shift should coincide with this base block B. So this is actually the same definition, only G replaced by X. And in the future, I just marked the required, not changes, but differences between the first part of my talk and second with blue, but I forget to mark this X with blue, but it is only the difference. Here should be the X inside instead of G. Okay, so next part, it is about difference. Difference is little bit changed. So difference here, as we can see, it is for base block B, its difference, it is a set of pairs. So this was the reason why we introduced this set X squared. So it is a set of pairs. gx, gy, which occur when we act on distinct points of similarly Cartesian product of b squared without the diagonal. So this is the difference. And this is the difference between the difference families over the groups and difference families over the G-spaces. Okay, so we can also adapt our property and call the base block full if its stabilizer is trivial. So this means that if you act with a group G on the base block B, you every time receive the different blocks. And the amount of blocks is the same as the cardinality of group G in this case. Okay, now the similar lemma that was also for difference families. So for any G space X and base block BC of X, two properties are satisfied. The first property is that difference of block B is equal to difference of left shifts of the block B. And second, it is that if differences are different and their intersection is not empty, then you break the first axiom of Euclid. This means that by action of G, of some element of G, you can just move this block B to some block that intersects C in more than 2 points, and these blocks are not equal. I suppose that I skipped it. So GB is not equal to GC. Oh, sorry. Okay. And this lemma motivates the next definition of a difference family. So very similar definition as I showed you for groups. That a family of base blocks is a difference family, but in this case, differences should cover not because we do not have group here, but they should cover x squared not equal. So Cartesian product without diagonal, and differences should cover it. So the change here is basically only this part. And again, the same definition of orbit. Orbit of base blocks, it is the family of its left actions of on the block B. And very similar to theorem that for any difference family B on a G space X, the pair that consists of X and the union of all orbits is a Steiner 2 design. So again, the similarity. And well-known example, I suppose that everyone knows that. So let F be a finite field of cardinality K, and X is equal Cartesian product F by F. It is a coordinate plane endowed with an action of the group of affine transformations. And let's take any line B of X. I mean the classical line, that line, for instance, of the view y equal ax plus b. And in this case, this singleton, just consisting of this line B, is a difference family, and the pair x and orbit of this line is a Steiner design infinite case that consists of k squared point, and every line contains k points. Okay, let's go further. Again, we can also similarly define minimality on the blocks. So minimal form of a block of G space X is the smallest element of its orbit of left actions on this block B in the lexicographical order on power set of X. So also very similar definition. There are only two differences that we replace it group G by X. And similarly, we can define a minimal form of a difference family. So also very similar definition. So a minimal form of a difference family on a G space X is the smallest element of a family. Same thing that with the groups. So we choose a minimal set, minimal family of transformations of this difference family, firstly by automorphism specific, and then by choosing a minimal element in every orbit in the lexicographical order of power set of X. So, as you can see, a lot of similarities. And again, the theorem, again, the same as for different families over the groups. So let be difference families on G space X. Then Steiner 2 design generated by B and minimal form of this difference family B are isomorphic. Okay, so using all these facts, we can define we are calling this algorithm Hetman-Banach-Ravsky algorithm. So, introduction of this algorithm. Let G be a group, H1, Hn be its subgroup, and this X distinct union of left coset spaces be a G space. Okay, then first observation, again, then let B be a family of base blocks with pairwise disjoint differences. So it is some kind of partial difference families. Then define difference of difference family similarly as union of its differences. And in the beginning, we can see that when we constructing the first next base block, it should start with AB, where AB is a lexicographically minimal element of this Cartesian product without diagonal and without this difference delta. Actually, it is delta B. Again, small mistake, sorry. And note that A is a minimal element of some coset space G left coset space to HY, which is a subset of X. So this is first observation. Then second, and this is the most changed part. So previously in state we used a base block, we used a difference, and we used a whitelist. So here it is completely different. So this is the most complicated part was to develop, and thanks to Taras and Alex, I was able to understand this thing and develop this algorithm. So now we define state completely differently. The same thing it is that it contains the base block. So let's state be a triple that consists of a block B. Then second thing that is needed, it's stabilizer S. And third part, it is the most complicated. It is a multi-valued function phi, assigning to every orbit G from XY its intersection with the set B squared without diagonal. So it is this phi is the most complicated thing, and invented was very, I would say, not obvious. And as previous algorithm for different families of the groups, algorithm consists of two principal ingredients. First is the function accept. But this function accept, previously it consumed state and the element X, and now it consumes also a difference of a current difference family. It is needed to calculate the next state of the block. And the other part is a recursive procedure search that is reporting difference families. Okay, as I told that this algorithm was developed together with Taras, Banach, and Alex Ravsky, and now we call it Hetman-Banach-Ravsky algorithm. Okay, here we have very complicated accept function. It is very actually complicated, and I developed and fixed bugs with it and enhanced it for a very, very, very long time until it came to its form. And basically, it is just simplified form of it. It is even more, much more complex. As you can see, even in this pseudocode notation, it is the whole slide. So it is much more complicated. Okay, so how we perform accept? So first of all, we consume a state. Second, we consume current difference of the current difference family, and consume the next element x that we would like to accept into this base block. So when we constructed the base block for difference families, we immediately added only one element, and every time we added one element. Here we are, when we accepting element to the base block, it can cause the addition of a very large amount of new elements. So this is the reason why we have here while. So what we do, we create a queue that consists of only this element x in the beginning, and then we are performing additions while this queue is not empty set. Because if we add element x, this base block already has some stabilizer, and in addition to element x, also other elements can be added. Okay, what we do then? We select a minimal element from this queue. Then we check if the size of the queue and the current block together have cardinality more than k. This means that this can be base block, but it is not a base block of cardinality k, so we can just show that this element x cannot be added. And also, when we need to add some element that is less than initially added element, this means that instead of adding this x, we can add this element q and receive the same result. So we do not need to repeat this calculation. Then we just return empty set, indicating that acception procedure was not successful. Okay, what we do then? Then we are iterating through the elements that are in this extended block B prime, and do the following. We simultaneously extend the stabilizer and simultaneously extend this function phi. So inside this algorithm, this stabilizer and function phi, they are kind of broken. They do not correspond to the final state that will be returned. But in the end, after finishing this while procedure, if we do not return empty set, we will return the correct state. So in this case, this block will correspond to its stabilizer, and this function will correspond to this block and to this stabilizer. Okay, so what we do there? So first of all, we need to extend stabilizer by intersection of BB and intersection QQ. So what is this vector notation? This vector notation shows the pre-image, actually kind of pre-image. So vector AB, it is elements of the group G such that action of G to A is equal to B. So because we are working in G spaces, this BB and QQ can be not trivial as well. So we need to extend stabilizer at first with this. Then second check if it can happen that pair BQ can be in the current difference. And using the previous lemma, in this case, this base block cannot together with previous base blocks form a difference family, then we also return empty set. Okay, then we do two cycles. First of all, we go through pairs AP, and secondly, we go through pairs PA. That belong to this function phi. that, let me remind this function, this phi is multivalued function assigning to every orbit j xy its intersection with the block. So we basically go through all differences that are now in this block, and when we spot that pair AP belongs to a specific already present intersection with the orbit, we also need to extend the stabilizer. So we're doing it here. Then we extend this function phi, adding the pair BQ and QB to the corresponding orbits. And in the end, we do the following. We firstly add Q to the block B prime, then it is just simplified notation. In the implementation, it is different. We close by the group operation the stabilizer, and we extend the Q with actions of stabilizer to left action of the stabilizer to the block B prime without this block B prime, because we already added the Qs from this B prime. And we are doing this until Q is not empty. And in the end, we return the updated state. So as you can see, it is pretty complicated. Okay. Then if we already implemented this accept functions, then search is actually pretty simple. So search is pretty simple, and it is also inspired by search of different families on the groups. So the same logic. If the size of block B is equal to K, then we just add this block to the difference family, extend the difference of difference family, and check whether it is equal to x squared. If it is so, then report the difference family and exit. In other case, this means that we did not cover all differences. And as noted in the beginning, we find the pair AB, which is a minimum of x squared without current difference. Then we accept to the single point block consisting of A. Obviously, this block will have trivial stabilizer, and it will have empty function of pairs, and we accept this B, because in this case, this block, even on 2 points, I suppose it can have even more than 2, no, or no, maybe it can even have, I do not remember, but just to be sure, and then execute search on this. In else case, this is the reason why we have here this delta. We are going through pairs. We are going not through pairs. Actually, we are going through pairs because we are going through pairs that are not in delta, and we have we are iterating through the possible pairs that minimal of block B and second element is not in current delta. So in this case, we are going through this axis, like that are not in the current difference, and just do the same. We are accepting to the state this element X, and if the state is not empty set, which indicates the incorrect state of state, then we recursively again execute search. So after the defining this very complex accept function, the search remains actually the same simple as it was previously, but in the updated notation. Okay, and let's glue it together. So gluing it together is again very simple. So let G be a finite group, H1, H8 be its subgroup. They form a G space X. Then we calculate, because we need to pre-calculate it in order to have fast calculations later. Cayley table for the group action, the group orbits on pairs, the two-dimensional array automorphisms of X. And then just invoke. First of all, we take the minimal element of X. Then we create the initial state. Then we create the delta that consists of only diagonal. Then we accept minimal element of X without M, because it should be done, and then because this difference should be covered, and then execute search. And that's basically the description of Hetman-Banach-Raski algorithm. And now this answers the problem which motivates this algorithm. So the following unitals cannot be generated by group difference families, but can be generated by HBR algorithm. So first of all, Hermitian unital can be generated by a G space, where G is isomorphic to second size simple group. It is PSL 3, consisting of 168 elements. H is any subgroup of G, and H cardinality is 6. And the reunital can be generated by this G space. So group in this case, it is 56 element semi-direct product. H is less than G, and cardinality of H is equal to 2. This also, by the way, explains why they cannot be generated by groups of order 28, because PSL and this semi-direct products, they do not have subgroups of order 28. And the automorphism groups of these unitals also do not have subgroups of order 28. This is an example and the explanation how these unitals can be generated. But these cases are very rare. I actually know only, I suppose, 5 such cases that we need to have bigger group in order to generate some design, but we cannot do it with a smaller group of the size of the number of points of the Steiner design. Okay. Now, again, optimizations and improvements. So the same trick with generating and storing first minimal blocks and then processing them parallelly can be applied. So this is the easy way to parallelize this algorithm. So first of all, let's assume that we generate only first base blocks that are minimal in sense of the difference families, and store them to files and read them from file and parallelly execute it. And this allows to utilize the power of multi-core PC. Okay. Second optimization is that because we are usually using the large group, that blocks containing some special differences could be unique or occur in very small numbers. So we find these blocks first and then generate the remaining difference families. So this already removes, adds some difference that will be used for filtering and removing correct states, and this helps also a lot. Blocks containing distinct points AC with orbits of AC equal to orbits to CA, they have non-trivial stabilizer immediately and can be pre-generated as well, and usually it helps also. Okay. Also about automorphism groups. Automorphism groups of group usually are not very large, except for some exceptional cases. In case of G spaces, the size of automorphism groups, if you have even 3 or 4 orbits, is usually very, very, very large. And sometimes you can just take special subgroup which will be used for filtering and use it, because otherwise you will just not have enough memory to store all this automorphism group. And next, I don't know how it is explained, but for some reason, if we have G spaces with generating subgroups are ordered in with their cardinality, but in descending order, they usually have smaller processing times. Sometimes the processing times can differ in 100 times for some reason. I don't know. Okay. And now about some results. And yeah, using this algorithm and some additional tricks usually, because in the beginning it was not so obvious, I was able to generate some new Steiner systems. And these are papers that have very self-explaining titles. So existence of this, and this Steiner system. Why this existence is in the title? Because we have a handbook of combinatorial designs, which has lists of, let me remind that BBD of VK lambda, VK1, it is the same as Steiner designs of 2KV. So there are tables for which existence of the Steiner designs remained undecided. And when I started working on this difference families and so on, I had a small dream. Just I want to find at least one undecided case and close this undecided case. And fortunately, I was able to close 6 of them. And yeah, these are preprints, but currently I submitted them to different journals, and it is very interesting whether this journal will take these examples or they will refuse it like it is some trash. So it is a moment of truth, and I'm actually checking these journals by these submissions. Okay. Then next, further investigation. So there was also one more place in handbook that left me, how to say, anxious. Because there are examples of Mills. It is a very interesting guy. He actually, you can see these lists here. For instance, for this table, before Mills, this table was like, I suppose, 3 or 4 times larger before he started his work. And he actually closed a lot of different admissible V's for the k equals 6. And he posted his papers just without an explanation how he did it. And Vedran also mentioned it. So it is very interesting how he did all these things. And I suppose that I have an answer, at least I have speculative answer how he did it, because next algorithm that I will describe you, it generates exactly the same base blocks that are in Mills' paper. Okay. So first example, it was establishment of this Steiner design. It was first example, Steiner design that has 6 points per line and 106 points in total. It can be generated but by very simple G space. It is Z53 space with 2 orbits of the same size and these base blocks, which actually is very hard to find. And second example of Mills, he also generated the same Steiner designs, but on design on 96 points. And this group, again, cyclic, but on 48 cardinality. Okay. So the G spaces actually are very simple, as you can see. They even do not need a notion of G spaces, and they can be, I suppose, explained using group approach. But the HBR algorithm requires several days to reproduce these examples. So in this particular case, it is very ineffective, HBR algorithm, because it is very generic. So to reproduce those examples, a specialized algorithm was developed for G spaces consisting of 2 orbits with a free action of the group G. So here we have simple group, cyclic group, and it has free action on its orbits, and this is how to say, this is the way how you can this offers you the ideas and optimizations that you can use. And let me explain this optimizations. So this part is very simple, and this is actually school arithmetic, and this part can be even explained to children in school. So to find the base blocks B, we first analyze the intersections L and R of these blocks with the orbits. And the restrictions arise from the structure of the differences, these differences, this, and this. And as you can see, this is very similar to the differences on the groups that I introduced previously. So it is just left. It is just a difference of left action of the group, and the same is for everything else. You can also see that this last difference, it is just inverse of this, and this means that one of them can be dropped, and this is dropped. Okay, now we have this specific table. So let L, it is the intersection. Let me go back. Let L, it is the number of points that are in the left part of the base block. R, it is the number of points that are in the right. So here you can see that L is equal 5, then it is equal 2, then it's equal 4, then it is equal 3, 3, and 1. And similarly for this design. And when you have the cardinality of left part, then right part, it is just K minus L. So this is the explanation of this school arithmetic. Okay, so let's assume that we have L, which is just a sequence of numbers less than equal than K, and they are in the ascending order. Then let's generate R. That is just K minus L. So children can fill this table very easily. So for 1 it is 5, for 2 it is 4, for 2 it is 4, for 2, 2, 2, 2, 2, as you can see. Then the middle column, it consists just of the products. Again, let's check whether children in school can multiply. And let's check whether they remember the multiplication table from the school. And here it is just L times L minus 1. It is, again, for children, you can just say, okay, let you have this number, remove 1 from this number and multiply and write into this column. The same is for right, as you can see. And let's check the sums. Sum here, it is 53. Sum here, it is 52. Sum here, it is 52. And let's go back to this difference. As you can see, that structure of these differences, it is L inversed times L without the neutral element. So group that was acting is Z53, and here we have this differences. So we should cover by the differences 52 actually differences. For differences between the orbits, 0 also can be included. So this is the reason why here it is 53, and this also 52 differences should be covered. So basically, if we have such situations that we have here 52, 53, 52, this means that using the base blocks that have such left side of cardinalities of left side and such cardinalities of right side, we can cover the differences here. Okay, and these sequences are not easy to guess. Actually, between all possible increasing sequences of numbers, there are only 3 possible distributions that satisfy this property that there is in this table. And this table shows one of three possible distributions of the cardinalities L and R for this space. And also, additional note that all base blocks in this G space should be full. I mean, with trivial stabilizer. It is impossible to have base block of cardinality K which has non-trivial stabilizer. So we will be building our difference family from base blocks. Okay, little more complicated is the case of 96. So the same table for 96, but let's check here. So as you can see here, the sum is again 48, but here sums are 42 and 42, not 47. Why it is that? It is because there are two mandatory non-full blocks that provide 5 differences each. Let's return back, and we can see this block 0, 8, 16, 24, 32, 40, and this. These blocks are, first of all, they cover the difference 0, 24, and 0, 24. It is in the same orbit than the difference 24, 0. And this is the reason why this block has non-trivial stabilizer. And actually, this is the only block in this construction that can cover this. And this blocks similarly. So we have this table. And in this table, in the end, we need to add 5 differences from the block of length 6 and 5 differences from the second block of length 6. And we receive in the end against 47, 48, 47. And yes, this is the explanation why we have initially 42. And again, after this school arithmetic, we can describe the two-orbit cyclic algorithm description. Okay, so we will use again the accept and search functions that were defined but for groups. And first of all, what we need to do, we need to compose the list of all possible distributions of cardinalities intersections of base blocks with left and right orbits. I mean, compose this initial left parts. Okay. Then, for each distribution from the list, generate all possible minimal difference families in the first orbit, just in the first orbit. And this can be generated by a group difference family algorithm that consists of blocks of lengths from the list. So, from this list. So, blocks now will have this length, not K. Then, we, for instance, store them somewhere into file. Or if it is not a large amount of them, then we can immediately go to the second step. And then we complete every left part by suitable right part, applying an enhanced accept function. And examples that using this algorithm, it was determined that the Mills design that was shown, it is a unique design generated by this G space. But for G space Z53, disjoint union Z53, there are actually 66 non-isomorphic designs, and I suppose that Mills, using some early supercomputer, he developed some kind of algorithm. He found this one first design. It was enough for him to close the case, and he left there because actually the full calculation of these 66 non-isomorphic designs, it took 1 month of CPU time on my home computer. Yeah, so even on the modern computer, but first design appears pretty quickly, and I suppose that was what Mills did. Okay, now let's go to the description of the algorithm. So enhance accept function. It is very similar to the accept function on the groups, but to the state we need to add additional 1 parameter. It is omega. Omega, it is because we have tracking outer differences between left and right orbit. And instead of block, it is only its right part. Also in accept, we need to put the corresponding left part of the base block. And the difference is pretty small. First of all, we need to calculate omegas, but we do not do anything with this omegas, we just calculate them. But this omega is important because it is used in the further part. Also, whitelist shrinks 6 times in this case. So it shrinks standard 5 times and shrinks 6 times. And let's go to the search function. So previously in the cyclic, not exactly generic group algorithm, to calculate initial whitelist for a specific block, we used delta. But we cannot use delta here. So instead of it, we are using this omega. So this is basically the difference between the difference family algorithm for group and difference family algorithm for two orbits. And how search looks like in this case. Very simple. First of all, we know we pre-calculated left parts. So it is just we have this lambda. It corresponds to a specific difference family that consists of left parts, minimal. And in this case, there are few differences. First of all, we calculate right parts of known cardinality. So this cardinality is k minus the corresponding left part. Then we finish when we finished all right parts. And then we cannot assume what points will be chosen for the right part. So we need to start from the very beginning. As you can see, we firstly calculate the whitelist, which is a complement to the left multiplication of left part to the omega. And secondly, we start from empty state. This means the state that corresponds to the empty base block. And we just for this empty state execute search. And here search is actually the same as for common group case. So we just iterating through the whitelist from some point and accepting the element, taking into account the corresponding left part of the difference family calculated. And that's basically it. And I assume that you can, using this, understand how to initialize this algorithm. But I just, how to say, as authors do when they do not want to write a lot of text and proofs and so on, there is a remark. It is possible to generate the algorithm for cyclic groups described above. It is actually about generic groups, but for cyclic groups, the initialization is simple, but for common groups, initialization is more complex. And this is the reason that you need to invent initialization for any group of specific order. You can also generalize this algorithm for 3 or more orbits of the same size, and you can also allow 1 or more fixed points or 1 additional small orbits. So these are possible generalization. I actually did this generalization, I suppose that even in the beginning of this year. And exercise, find algorithm for the above generalizations. I assume that using the slides, you can easily develop the generalization for all these 3 cases. And using this generalization was found one more example. So Mills generated the 2-orbit design for cyclic groups. But I was able to generate 3 more for specific small groups from GAP. So this small groups also admit one more design, and the most interesting is this one, because it is just this 4828. It is binary octahedral group. It has name binary octahedral group. I don't know whether it means something, but these groups are just some semi-direct products, and this is a binary octahedral group. It is actually very interesting. And results regarding this last algorithm is in this paper, also submitted to arXiv. And final conclusions. So here are described the very basic ideas of algorithms. in practice, different cases often require suitable modifications of algorithms. So these algorithms are just the basic ideas, and using these basic ideas, you can just regenerate, for instance, examples from the handbook of combinatorial designs. To go further, you need usually to have some enhancements, some improvements, some take into account some assumptions, and so on. Also, because there is a lot of algorithms, I explained it here, maybe 5 algorithms, but in my code there is like maybe 12 different algorithms, and but yeah, they following the same basic idea. But yeah, they require slight modifications, they require some assumptions, and so on. So you cannot just like, I don't know, create a package, include it, for instance, into GAP, and my dear friend, I gave you this package, now you just enter the parameters and magically it will generate. Unfortunately, in my case, it is not working like this. Okay, and in the end, algorithms described above reproduce almost all examples from Handbook of Combinatorial Designs. Actually, the rare cases that are not reproducible, I don't think that they even, how to say, needed to be reproduced by these algorithms. They have some other specific algorithms that can reproduce them more easily. So for me, it was end of ideas. I do not have, unfortunately, now the source of how to reproduce this, because I actually now know how to reproduce all these examples. Yeah. Also, the one more thing, that a lot of possible constructions produce nothing. So usually how my work is proceed, I am just assuming, okay, let me try this construction with this algorithm using these assumptions. Then I launch the search can even take 1 or 2 CPU days, and in the end I have nothing. And this result, actually you can publish it like when you have such constructions, such groups, such orbits, and so on, you have nothing, but this is it. And for this results that I showed in examples, there is, I suppose, even maybe 1,000 of tried constructions which produce nothing or nothing new. The main issue at the moment is to find suitable generating group and orbit structure. So this is a very big problem for me, because Vedran mentioned that there was a Yanko who could just guess, let's try this group, and usually this group generated something, and I was lucky to guess a few times to generate something, but yeah, I would like to have the Yanko talent to guess the groups better. And in some cases, the complete search can be skipped after a simple preliminary analysis. This means that sometimes the structure of the space, structure of the group, or so on, it forbids the existence of a design admitting this group F as a subgroup of automorphism order. And yeah, that's it. Thanks for your attention. Here is a link to my GitHub, but as I mentioned previously, it is not a factory, it is a laboratory, and in this laboratory, to reproduce the examples I show, you need to understand the code and you need to adapt it to your computer. So this code sometimes works just by launching, but sometimes you need to adapt it. And yeah, that's it.
Thanks for a nice presentation. Yeah, let's first ask the audience whether there are any questions.
I have a question.
Okay.
Ivan, is it true that whenever you find a Steiner design with new parameters, then you automatically find strongly regular graphs with new unknown parameters?
Yes, it's completely true. That was the reason why we earlier invited you our seminar, and I wanted to know how to find automorphisms for these graphs, but since that time I integrated with Nautian traces, and currently I have Nautian traces under the hood and can find automorphism groups of these strong graphs. But yeah, the Steiner designs, they are symmetric and regular because usually they have very large automorphism group.
Okay. And another question. If for new parameters you construct a Steiner design, is it typically unique or there are many?
It
Not
depends.
isomorphic. I mean, not non-isomorphic.
Yeah, I understand. So usually with these constructions, for instance, here you can see that for each group there is exactly one design. But when we are talking about their presentation as difference families, usually the number of difference families is large. For instance, I remember that for these designs, each of these designs is represented by difference family for like from 10 to 30 times, and you just need to filter these difference families and collect non-isomorphic. Sometimes there are some constructions that there is a correspondence one-to-one. So you get one difference family, and this difference family corresponds to one design. So it depends on the group, and I do not know what causes it, but my regular activity is just, firstly, I generate all difference families, then I filter them and analyze what was generated.
Okay, thank you.
Anyone else before I ask a couple of Taras?
I have some comment. I looked at the internet and asked artificial intelligence. So this binary octahedral group, it is a symmetric group of four-dimensional regular polyhedra, actually.
Yes. Yeah.
And
I also seen that. I also have seen that, and this is the reason why I, how to say, specifically emphasize it on this design, because I would like to know and understand whether it's somehow related to this polytope. This design is somehow related to this polytope.
So that was the question. How this design relates to this polytope? So
yeah, I don't know. We can, for instance, how to say, state a problem, find the relation between the found design and this regular polytope and how they are related. It can be something like the isomorphism between PSL 3.2 and PSL 2.7, something like this.
So this polytope probably it is self-dual, right? So you have 24 and there is dual polytope which also have 24. Maybe those are two orbits probably. I don't know.
Yeah, I don't know either, but yeah, this is actually a very interesting question, and I suppose that we can even discuss it offline, for instance. Or
okay, thanks.
Yeah. So for now, I do not have answer how they are related, but I suppose that there could be some relation, and maybe it can lead to some another discovery.
Okay, could you show us the table, this cool table with distributions of lengths of blocks in case of this octahedral group, I mean.
This table for the case of this octahedral group, it is not this table, because this octahedral group, it has, as I remember, more than two blocks that have non-trivial stabilizer. So what is the algorithm for this, for the generation of this octahedral, design? Firstly, you calculate all blocks with non-trivial stabilizer. Then you calculate how many differences they cover in left, right, and right orbit. then you remove these numbers from 47, 48, 47, then you calculate the school arithmetic for these remainders, I mean the length of lefts, then you generate the difference family, and then for left, and then you by just difference family generate the right. So this is a generalization that is a little bit more complex. So it does not correspond to this table for this specific case.
I have in mind maybe there is some symmetry in you producing some design, right? You have answers. What are intersections of your blocks with left and right orbit, right? And is there any symmetry in this data? So, for example, there is as many left intersection as right intersection, something like this. So just to look at the table from, you calculated already this.
It is symmetric. So in this symmetric left, it is just right, but rotated back. So if you remove from left the right, this gives the same numbers. For instance, here there are different numbers, and these distributions have two cases. First case is when left is not equal to right, as I said, and second, if left is equal to right. And especially this design, it has such properties that in this case, left is equal to right, and it is interesting property. So I suppose that maybe it has some internal symmetry inside it, but automorphism group of the design is only 48. It do not have additional automorphisms.
So you cannot switch between orbits, right?
No,
there is no reflection.
You cannot switch between orbits, because in this case you would have additional automorphism, and this design have not additional automorphism. Its automorphisms have two orbits, and these orbits cannot be exchanged.
Okay, thank you. Very interesting.
Okay, may I could you please just return to the school arithmetic, since you were just discussing it? It might be that this school arithmetic is actually somehow related to Dembowski's equations that I mentioned in my talk. I guess this could be like something like the candidates for the columns of what we call an orbit matrix. So I'm pretty curious.
Also, one more thing I can show you, because we have time, because I finished a little bit earlier, and that was intentional, because I have something to show you. Wait a second, I will show you. I mentioned that sometimes you can just perform a preliminary analysis and do not try even to generate this design. So here it is my file with this preliminary analysis. For instance, you can see the distributions of this school arithmetic for 96. Yes, you can see this distribution for school arithmetic for 106, and I stored only 5. So if there is 5, there can be more than 5, but if it is less than 5, it is less than 5. And you can see that, for instance, case, let's scroll further. For instance, it is impossible to generate both 85.7 and 91.7 with two orbits. And it is impossible to generate 91.6 with two orbits of length 45. This is what it means. So maybe it is related, but I just came to these equations just by myself. I assume that they were invented earlier, but and it is also calculated for 3 orbit cases, because I have now generalization for 3 orbits, and also these are the possible distributions of like left, middle, and right. Left, middle, right, left, middle, right, left, middle, right, and so on. And I even went to 4, but the calculation takes more and more time.
Dembowski's equation work for any number of orbits, and they basically, if you have a 2D design, these are some quadratic equations. we were kind of always looking at the full orbit matrix, but I think what you're doing is just taking one column and taking the possible values that can occur, which does. I will have to think about it a little bit, but somehow I think that this might be related to these equations. But actually, what I wanted to first comment a little bit is that I was a bit awestruck by this G space notation, but yeah, well, I was using it's actually the same, it's just a little bit different language. So what I didn't even know that the term was G space. It's just a group action. It's a group acting on a set. And
I
this is
did not know it as well. It was
is it
by
from
Taras.
Cameron's book?
Taras know about G
Where
spaces,
does
and
the term G space come from? I might have heard it. I just never used it that much. Do you know? Is it from Cameron's book or for for someone else?
I suppose Taras can answer this
Okay.
because I'm
So anyway,
less qualified to do this.
I was kind of yeah. Taras, do you know?
I can try to explain. So, as far as I understand what's going on, so there are just two cultures in mathematics. One is continental and other is island, let us say. So one has origins in Europe, like France, Germany, and the other in Britain. And they speak about the same thing by different languages. So Britain, they like permutation groups, right? And Cameron is answer from Brittany, so they just use subgroup of permutation. It's efficient, very nice language, very nice results, etc., etc. And the language of G spaces, it is more common in Europe, as I model the situation. And also there are two schools or two cultures of acting these elements of the group. So they can act from the right or they can act from the left, and again the same situation. So if you accept some functional point of view on this group, so function usually in Europe at least they are written from the right side, right? So they in this sense we should prefer left actions because you write function from the left and then parentheses, arguments, etc. But computer scientists and algebraists, they usually accept this opposite, which is more natural, because it's also distinction between direction of driving in the country. So we have England system and French system. So right hand preference or left hand, and this also always reflects in such. As for me, it is a kind of catastrophe, of course, in mathematics, because we have no unit points of view on the same things, and it of course, gives us possibility to discuss what is better, what is worse, but that's such historical situation.
Well, I wouldn't call it a catastrophe, but it is exactly the same thing. A permutation group is just a group with an action. So that's, well, okay. Group actions are a little bit more general because you have these non-faithful actions, but this is actually not important. You can just
question where you start, right? Or you start from groups or you start from X. And
yeah.
if you are starting from X, you are in the ideology of German school of Klein geometry. So you have at first geometry, and then you ask what are automorphism group which acts on this X, right? But if you accept group theoretical view, so you have a group, and then you embed by Kelly's theorem to symmetric group, and you so again it's the same situations. It's very, very interesting civilization question how it happened, and maybe it is fruitful also because there are two points of view on the same subject. You can derive different conclusions. It's not maybe not so bad as we can suggest.
Well, I've never made the connection with continental versus island philosophy, but you know there are many books titled permutation groups. For example, one is by Huppert. It's German, so I don't think that it's so geographic. There are certainly several cultures or several ways people talk about it, but I don't think it's catastrophe. It's a very simple connection once you realize it's the same thing. But what I wanted to ask Ivan is First of all, since these new designs, did you also check there are recursive constructions? So when you find one, you might actually be able to eliminate several ones by these recursive constructions.
I eliminated one by recursive construction. So after constructing this, I eliminated this by recursive construction. The whole set of lines, it only for one design, it takes 8 megabytes of space. Just to have the lines for this design, but I uploaded it
It's a big
to GitHub, and anybody who is interested can download the slides and check that this is indeed the Steiner 3321 point Steiner design.
And another thing, as Oleg already mentioned, whenever you have a new Steiner design, you automatically get a new strongly regular graph, and there is Brouwer's table. Do you know about Brouwer's table of parameters of strongly regular graphs? Also, with some,
by the way, no.
You should probably write to Brouwer that you have new. I don't know about. I didn't look. Which sometimes it happens that the graph is already known. So graph with this parameter does not necessarily come from a Steiner system. But I guess since you have at least 6 of them, I guess that probably some of them have not maybe been known. So this is one worthwhile thing, that check Brouwer's table and see whether you eliminated the question mark and write to Brouwer, and he will put a link to your preprints at least.
Okay, and I suppose that you can send me the email to this website or whatever, and I will take a look on it. Okay.
Another group of people who might be interesting, there is a repository of coverings. Coverings are, well, they're just a generalization of Steiner 2 designs. And Steiner, whenever you have a new Steiner system, this is optimal covering. So they also update, you might have broken some of their records too. So I will send you the links, and then, people will know about the new results, because these new results, whenever you have a Steiner system, automatically you get a lot of new stuff people that are interested in, actually. So I think these are very nice results, and you shouldn't be too worried that some journals are a bit snobby, might not want computer-generated result. My experience is you just send it, if you get a rejection, you send it to another journal. So
in the morning, we received for, I suppose, this paper, the review, and the review stated that paper was written somehow in a bad mathematical language related to this area, but results are so strong that they cannot refuse it, and they just they told how we need to improve this paper. So yeah.
But anyway, congratulations then, for at least a positive review, or not so negative that it's rejected. Yeah. So it's a way, it's a learning curve. Mathematicians are often very snobby. So that's kind of.
I understand this, and I'm completely fine with it. But for me, it is just more, little bit more test. What will be the consequences then? Some tragedy that, oh my God, somebody refused my paper. I actually don't care about it. I uploaded all papers to archive. My results are present. I suppose that if, as you told, they are useful for graphs, for coverings, and so on, then eventually somebody will note them and analyze them. So yeah.
And I will upload a recording of this seminar to YouTube, so you can share distributing.
Okay, I will help.
Yeah. Okay. Any other questions?
YouTube mathematician with 1,000 of views.
So I can add that both reviewers suggested to remove exclamation mark from the title.
Oh, that's a pity. You
it
know,
was not intent.
I think that the people from Bayreuth, I very much like the fact that they published this short one-page paper with exclamation mark in the title, because yeah, I think it's a nice title actually, but yeah, some people might not want
Resembles me.
any emotions in mathematics, I guess.
There is a
Okay.
story about Joseph Stalin. So he had a meeting in the Kremlin, and he said, "We have two questions to discuss. One question: kill 10,000 people. And the second question: recolor Kremlin from the red to the blue." And they
And nobody
was,
asked anything about the first.
why we should recolor our dear Kremlin in blue? It should be red. Okay. So I knew that you have no objections concerning the first question.
I heard about it. Yeah.
Yeah, so
Okay,
the
any
same.
other questions related to Ivan's talk? I'm going to stop recording. I just want to let me